for a search. It's expensive. Like if you want to match the last 30 bits, you got to do like 2 to the 30 time probably on your classical computers, which is a lot of work. Lots of some work. So that's what Bitcoin does, and it sort of proves that you've put in this amount of work, and it makes it hard to lie because you have these hashes written. Okay, so anyway, the best classical attack on this is essentially trying everything on the SHA function. You can try every possible preimage and find the one that works. So if somebody gives you Z, you get X that hashes the Z. Of course, it's highly parallelizable. So you can do it on your GPUs, or you can just buy a million GPUs and run them all. Partition the input space into a million different pieces and run them all in parallel, trying to guess a preimage. So 2 to the 256, and it's kind of a large number. So the number of Planck time steps since the Big Bang is 2 to the 207. So it's a lot longer than the age of the universe. No matter what your clocks, no matter how fast your computer is. Okay, but I guess the number of atoms in the universe is 2 to the 270. So if you parallelize it across a significant fraction of the universe, maybe you'd be all right. Anyway, it's a pretty hard question. But we can do a lot better quantumly. So what we can do quantumly is we can do this. So you can create a uniform superposition over all possible input strings. You can compute the SHA function in parallel, in quantum parallel, in superposition on each of them. So that gives you this superposition where I've entangled X with this SHA hash. Of course, that's useless because if you measure this register, you just get a random hash. You don't get the one you're looking for. So instead, what you do is you run Grover search algorithm, or amplitude amplification, right? So the stupid algorithm is you guess a random X, and you evaluate its SHA hash, and you check whether it's correct. So the success probability is 1 over 2 to the 256. Using Grover search or amplitude amplification, it's square root of that, so 2 to the 128. Which is still quite a lot, but it's square root faster. So, I don't actually know what the numbers are for Bitcoin these days, like what K is. So the complexity would be 2 to the K classically, 2 to the square, 2 to the K over 2 quantum. Okay, so here I just say be careful. So this 2 to the 128 is not the same as the 2 to the 256 because, I guess, so 2 reasons. One is that a quantum computer, which doesn't even exist, but if it did exist, it might run at a different speed than your classical computer, right? Because your classical computer is running at gigahertz speed, which is about 2 to the 30. Giga is 2 to the, mega is 2 to the 20. Giga is 2 to the 30 per second. Whereas, for example, an ion trap is running at about 2 to the 13 operations per second. Different devices are faster than that. Like a superconducting qubits are probably 2 to the 15, so 2 orders of magnitude faster or something. But still, it's slow down compared to here. So that gives you a 2 to the 15 difference between quantum and classical.
Oh, what is theoretically, like, how many hops could we have in a second? Like, just appealing to physics, like, what is the upper bound on that?
I don't know. I guess it's probably Planck's time, right?
Planck's time, right? Yeah.
Yeah. What is Planck's time?
I mean, whatever Planck's constant is, what, 10 to the negative 34 or something?
So is it?